Welcome back to lecture 6 today. So in the last lecture, lecture 5, we introduced the concept of heterojunction, abrupt and graded heterojunction, also about lattice mismatch and how you need to have materials that are of the same family with minimal lattice mismatch to be able to grow heterojunction. And heterojunctions are very important for a lot of RF devices that are in the market today. So it's very important to understand the concept of heterojunction. Today we will try to conclude the concepts of heterojunctions as required for this class, and then we will introduce the concept of gallium nitride, polarization and the III-nitride alloys, which will help us understand how high electron mobility transistors work. In fact, we will also give a very quick glimpse of a basic gallium nitride high electron mobility transistor and how it works, so that subsequently when we come to the week of gallium nitride HEMT discussion, it will become easier for us to understand if we have the background today. Okay. So over to the whiteboard now. So today is lecture 6. Okay, lecture 6 we will try to wrap up the heterojunction things that we talked about. So just to have a recap from last lecture, we talked about graded heterojunction, where the heterojunction can be graded like that. This is say gallium arsenide and this is suppose aluminum arsenide, and the band gap is graded gradually. So an electron which is here can roll downhill in this direction. So the field is in this direction. Okay, this is the field for electron. A hole which is here can roll downhill like that. Okay, so the field will be in this direction for holes. So you see in a graded heterojunction, the field for electron is in this direction. Okay, the field for holes is in this direction. Both are in the opposite direction and their magnitude could be different depending on the slope of the heterojunction in this graded region. So this is very fascinating because you can have electric fields separately of separate magnitude and separate direction for both electrons and holes in the same region of space, which is otherwise impossible in a homojunction, because if you have a silicon homojunction like that, electron will roll downhill like that. So their field is in this direction for electron, and a hole will roll downhill like that. So the field is in this direction for hole. So both electrons and holes have a field in this direction only. Okay, so this is the beauty where you can individually tailor the magnitude, okay, as well as the direction of the electric field separately for electrons and holes in a heterojunction. This is one of the beauties of heterojunction. So now, because heterojunctions depend so much on alloys, okay, whenever we talk about alloys, it's basically mixing two or more different compounds. So I have, for instance, indium gallium phosphide, where I am mixing x amount of indium and 1 minus x amount of gallium. Now the lattice constant of suppose indium phosphide is some quantity, and lattice constant of gallium phosphide is some other quantity. So if I have say 40% indium and 60% gallium, this compound, how much will its lattice constant be? So people use something called Vegard's law. In this case, Vegard's law states that you linearly interpolate between this. Suppose you have x amount of indium and 1 minus x amount of gallium. So x amount of this quantity, which is A indium phosphide, plus 1 minus x of this quantity, which is A gallium phosphide, this quantity will give you the total lattice constant of indium x gallium phosphide. You got it? So if this is suppose 4 angstrom and this is suppose 4.2 angstrom, and you are talking about indium say 60%, gallium say 40%, then you are talking about 0.6 into 4 angstrom plus 0.4 into 4.2 angstrom. This total, whatever angstrom you get, is the indium gallium phosphide with 60% indium, 40% gallium, that compounds lattice constant. So this rule, Vegard's law, also applies to things like dielectric constant you can extrapolate, effective mass you can extrapolate. Okay, typically most of the parameters people extrapolate except band gap. Band gap you typically cannot linearly extrapolate because band gap has an extra parameter called a Boeing parameter. The band gap does not linearly change with the composition. So what I mean is that if I plot the band gap here and the lattice constant here, it is not a straight line like this, it is a bowed line like this. So, okay, so there is a Boeing parameter, it does not go linearly, okay, typically it does not go linearly. So, there is a Boeing parameter because it is a very complex dependence. It also depends on the method of growing, the way you grow some compound in MOCVD or MBE, the band gap could change, and whether you are measuring the band gap using optical method or electrical method, it could give different results, So, that way there is a lot of complexities there, so it does not go linearly as much, okay. So, this is an important and interesting concept to understand. And the last thing that we should definitely know about in heterojunction is the something called quantum well, okay. Typically quantum well is in high school or in 10+2 we all study about the particle in a box, it is the same thing, the particle in a box. What we study about this kind of thing in our 10+2, where this is your potential V naught suppose, and this is a well. So, this well thickness is suppose A, and this is a very narrow well. So, you have discrete level n equal to 1, n equal to 2. Remember, if it is a infinitely deep quantum well versus a finite quantum well, you have different wave functions. So, this will be suppose a wave function like that, this will be suppose a wave function like that. You remember, and then 3 you will have 3, you remember all this, right. So, these are discrete levels of energy E1, E2, E3. So, energy levels are discretized. The electrons can take only discrete levels of energy, and if it is a finite quantum well, this is a quantum well, it is confined, then electrons can also then tunnel across the barrier, it can tunnel to the barrier, okay. There is a finite probability of the wave function tunneling. If psi is the wave function, then psi square gives you the probability of the electron being found in a certain location. This we know about, but this is in practical, in reality this is actually realizable using a quantum well. So, what I mean is, suppose if you have aluminum arsenide, you have gallium arsenide, and again you have aluminum arsenide. If you join them together, ideally they should look like that, okay. So, it should be same of course. So, this is a quantum well, okay, because it has discrete levels like that, it is a quantum well. But this thickness of the layer A, for instance, or you can say D, this thickness cannot be very thick. This has to be in the order of the de Broglie wavelength of electron in the material. So, the de Broglie wavelength or de Broglie wavelength in a material is basically h by p, p is the momentum. So, that is 2 pi h bar by momentum is basically given by square root of 2 times effective mass into energy. So, you can find out actually depending on the effective mass of electron, you can find out the de Broglie wavelength. If you have lower effective mass, say gallium arsenide has 0.06 m naught, that is the effective mass of electron in gallium arsenide. So, your de Broglie wavelength could be 80 nanometer or 100 nanometer, something in that range, okay. So, this width of the quantum well, okay, this width of the quantum well should be less than around 80 or 100 nanometer, in which case you will get quantum confinement. Beyond that, it is basically not a purely quantum confinement. In gallium nitride, for instance, effective mass is 0.20, and so this is around in a 30 nanometer range. So, it should be less than 30 nanometer to get quantum confinement, okay. Typically people use few nanometer for pure quantum confinement, but this quantum well is an important concept in RF devices because all the high electron mobility transistors are based on the electron gas or the electron channel exists in a quantum well kind of a region, okay. That is why it is very important. So, this quantum well that we talked about is a square quantum well because it looks like a square or rectangle, square quantum well, and you can see that what we studied in our 10+2 physics or undergrad physics is practically realizable using, for instance, an aluminum arsenide, gallium arsenide, aluminum arsenide heterojunction. It could be any two wide bandgap material, in between there should be a narrow bandgap material. So, it will look like that, okay. So, that is why there is a quantum well of electron. By the way, there is a quantum well for holes also here, but RF devices typically are unipolar. Unipolar means that there is only one type of carrier, which is usually electron, because holes are slower, they have lower mobility, and you do not want those kind of devices typically, except for HBT in your high speed RF devices. HBT is a bipolar device where holes are also important, by the way, but in unipolar devices the quantum well in the hole in the valence band does not play a role because there is no hole, there is only electron, okay. So, this quantum well is a very important concept, and in the growing of the quantum well also you have to still consider lattice mismatch. You cannot arbitrarily grow two very different, widely different material to form a quantum well. Theoretically you can, but practically you cannot. People can say that indium antimonide has a very small band gap and say aluminum nitride has a very indium antimonide band gap could be maybe 0.1 electron volt, aluminum nitride band gap is 6.2 electron volt. So, if 6.2 electron volt is like that, okay, then 0.1 electron volt will be like that. So, it will practically look like this. Imagine the kind of quantum confinement, okay, it will look like that. See how many levels you can get here, because this is indium antimonide and this is aluminum nitride. This is theoretically you can do this, you can also do Silvaco or any other Centaurus TCAT simulation to find out different properties, the device, etc. You can get beautiful characteristics of a device based on this, except that it is not practical, impractical, because you cannot grow lattice matched planar epitaxial crystalline indium antimonide on top of aluminum nitride. They are of different material families, they are not the same structure. Okay. So, all those things you need to keep in mind. So, this is in a nutshell the concept of a heterojunction, and heterojunction is needed for a conventional 3-5 semiconductor for HEMT. HEMT could be also pseudomorphic HEMT, okay, or metamorphic HEMT, but we will come to that little later. And it also needs about HBT or heterojunction bipolar transistor. In these categories of devices we need heterojunction, and that is why we talked about heterojunction. HBTs and HEMTs, they have different pros and cons and they are different applications, and they are still very much used in today's RF systems and circuits, as we discussed in lecture 3 and 4. And gallium nitride is the other semiconductor family, we call them the III-nitrides. Okay, we call them the III-nitrides, they also have HEMTs. We do not call pseudomorphic HEMT, metamorphic HEMT in gallium nitride family. We also do not have HBTs in gallium nitride family, although academically people have researched there are HBTs that are reported, but practically HBTs in gallium nitride family is not very promising as of today, and people are still working on them, but there is no commercial or there is no possibility of a commercial device of HBT based on gallium nitride in the very near future. Okay. Now, the basic underlying principle of a HEMT, although we will talk about HEMT in details in one of the weeks, but the basic concept of HEMT, and I will not exactly go into HEMT now, is that you have a wider bandgap material which is suppose aluminum, gallium arsenide, and then you have gallium arsenide. Now, if you do not dope them, and you can mildly n-type dope them, so it is here, it is here. So, if you join them together, okay, if you join them together, what will happen is that the Fermi levels will align. So, this will come down, this will go up, but the points are frozen, correct. So, this point is frozen, this point is frozen, this point is frozen, and this point is frozen. So, when it goes up like that, it will look like that, it will look like that, and it will look it will come down. So, it will look like that, it will look like that. Okay. So, what will happen is that you have a Fermi level which is equilibrium, it stays constant, and it looks like that, like that, okay, this way and then this way. This is your heterojunction, actually L-gas-gas heterojunction. This is not HEMT, but you can see that this spacing between the conduction and the Fermi level tells you how many electrons you have. The further this is like this, the fewer electrons you have. So, this is like a almost depletion because electrons are fewer there. However, this region, if you look at this region, it looks like this, okay, it looks like that. So, you can see that this part is coming fairly close to the Fermi level. This is Fermi level, this is conduction band. If this conduction band is coming fairly close to the Fermi level, which means there is a relatively high concentration of electrons at that point, still not high enough, still not high enough. If I can make this conduction band cross over the Fermi level, what I mean is that suppose this is my Fermi level, and if I can somehow make this go like that, that means this is a conduction band, the conduction band has gone below the Fermi level and come up. What it means is that your Fermi level is on top of conduction band. So, this part, okay, please note carefully, the Fermi level is above the conduction band. What it means is that this is a degenerate electron gas. Okay, degenerate electron gas, which means this is super high concentration of electrons, because the conduction band has gone below the Fermi level. The Fermi level is above the conduction band. This is a positive quantity. The Fermi level has gone above the conduction band. From basic semiconductor physics, this is a degenerate electron gas. So, this is a very high density of electron gas that has formed. Okay, electron gas it has formed, and we call it the two-dimensional electron gas. The reason is because it is bound in x and y direction, but cannot move in z direction. What I mean by that is that if this is your Fermi level, okay, and this is your heterojunction, I am not drawing the valence band here, just the conduction band. This is actually a triangular quantum well. This is actually a triangular quantum well, where this is a barrier. This is delta EC, this is a barrier, and on the other side there is a barrier. So, it is like that. This is Fermi level, and it could have subband 1, subband 2, two subbands could be there, or two discrete levels could be there, and this is a quantum well, not an infinite quantum well, because this is a finite, this is finite. So, this is a finite triangular quantum well. Okay. And this is the z direction, which means this is the z direction, this is the direction in which the material is being grown. This is the growth direction, or the direction in which the material is being grown. Okay. In this direction, the electrons that are here, the high density of electrons that are there, cannot move in this direction. So, these electrons cannot move in the z direction, in the growth direction it cannot move, because there is a barrier, it is a quantum well. It can only move in the x and y plane. Okay, this is energy, but in general what happens is that if I take a stack of say L gas, aluminum, gallium arsenide, this is the cross section, this is gallium arsenide, then the electron gas is here. It cannot move in this direction, no, in the z direction it cannot move, it can only move this direction x and this direction y. It can move in the xy plane. So, it is called two dimensional, because it can move in two dimensional plane only, it cannot move in the third dimension, the z dimension. Why? Because it is confined by this barrier. So, it can move in two dimensions, so it is called two dimensional electron gas. Okay, it can move in two direction, okay, x and y, and you can make a transistor based on this. It is called high electron mobility transistor, because the mobility of electron in that 2D electron gas triangular quantum well is very high. It can be easily more than 10,000 centimeter square per second, which is very high. At low temperature it can go much higher, 50,000. In fact, at room temperature itself it can go much higher. Okay, and at low temperature people have gone up to really high numbers, very high numbers, 100,000, more than that. What it means is that your electron mobility is much higher than that of say silicon, where the electron mobility is around 300 to 500 or maybe 700. Compared to that, 10,000 is a ridiculously high number. So, that is why it is called high electron mobility transistor. The mobility being so high is a greatly advantageous situation for RF devices. Higher the mobility, better is the device in general. It also has very high velocity, okay, about 2 into 10 to the power 7 per centimeter per second. So, it can make really high speed RF devices. So, this is the concept of high electron mobility transistor, but how will you make this quantum well? You will make this quantum well by using a concept of modulation doping, which we will discuss in the week that we discuss about gallium arsenide HAMTs. Okay, that will come little later, but modulation doping is the technique with which you make this triangle quantum well, because without that you will be with this, where it goes like that, but you want the notch to go down. So, that is by modulation doping. Okay. So, that basically brings us to the conclusion of the heterojunctions part. Now, we will move into the gallium nitride section. Okay. In this lecture 6 we will move to gallium nitride and its alloys. This is also heterojunction, by the way, this is also heterojunction of course, because gallium nitride family has three material, aluminum nitride, gallium nitride and indium nitride. Now, typically they can crystallize, or their crystals are typically they fall into something called woodside crystal structure. There is also a cubic phase, but that is less studied and that is not used for any RF device today commercially. It is only woodside phase of gallium nitride family that is used in RF devices, and woodside is, you can think of this as a distorted hexagon, So basically, you know, you have a hexagonal kind of a lattice, the lattice is like a hexagon, okay. It is still a slightly distorted hexagon. So hexagons have a, you know, if you look into the hexagonal crystal structure, okay. So there is a lattice constant along this direction called C. This is the C lattice constant is in the vertical direction and A lattice constant is in the lateral direction. So C by A ratio, the C by A ratio for a perfect hexagon is 8 by 3 square root. So in the case of gallium nitride crystal, it is slightly distorted compared to a square root of 8 by 3. So it is a distorted hexagon, okay. It is a slightly distorted hexagon, and so this direction is the direction in which the material is grown, okay, and this is the Z direction, and this is called typically 0 0 0 1, okay. This is the 1 stands for the C essentially. So it is 0 0 0 1 direction in which this is typically grown, okay. This has a band gap of 6.1 6.2 electron volts, this is ultra wide band gap, this is 3.3 to 3.4 and this is around 0.6 to 0.7, okay. They are all direct band gap material, so they can emit light and they can detect light very easily, okay, direct band gap. And you can mix and match alloy and you can form aluminum gallium nitride, for instance. You can form indium gallium nitride, which is used in all kinds of white LEDs today. You can form indium aluminum nitride. You can also form indium aluminum gallium nitride. So if you have 4 of them, it is called a quaternary alloy, okay. Otherwise it is called ternary alloy, okay, ternary alloy. And for simple things like lattice constant, effective mass, dielectric constant, you can still use Vegard's law. You can use still Vegard's law that we discussed. However, for band gap you cannot use Vegard's law, okay. Now this is fine, this is fair. This gallium nitride and families are, gallium nitride is a wide band gap material, WBG, because 3.4 3.3 electron volt is a very wide band gap, and this is ultra wide band gap. Of course indium nitride is not wide band gap, but indium nitride is not so much used in RF devices. It is used in optical devices to get blue or green emission, blue LED, green LED, laser diodes, white LEDs, okay. But in RF devices typically aluminum and gallium nitride are used, sometimes indium could be also used, okay. Although I do not know of commercial devices that are yet up there which contains indium nitride in RF devices today, okay. Now the difference with other III-V semiconductor or silicon, or germanium is that gallium nitride family has a particular property called polarization. What it means is that there is each bond, you know, each bond is a polar bond. So there is a each unit cell will have a dipole. Let me make it clear. Suppose you have a gallium atom and you have nitrogen, tetrahedral, okay. So the bond between gallium and nitrogen, the electron cloud that is shared between gallium and nitrogen is asymmetrically distributed, so that nitrogen is slightly negatively charged and gallium is slightly positively charged. Now this asymmetrical distribution of electron cloud that gives rise to this partial positive and partial negative charges on gallium and nitrogen atoms respectively, okay, happens because of 2 reasons. Reason number A, it is woodside, which means it is distorted hexagon, okay, it is a distorted hexagon, okay. So the total polar bond, you know, the polarization across each bond does not add up to 0 when you look in the Z direction. Second reason is there is a very high electronegativity difference between the atoms. Electronegativity difference is pretty high among the atoms, and the fact that there is a woodside distorted crystal, both of these factors combine to lead to a non-zero polarization in the Z direction. We call it out of plane. Anything in Z direction is called out of plane. So in outer plane there is a non-zero polarization, I call it sigma. In plane is xy direction, in plane the polarization is 0, there is no polarization. Only in outer plane there is polarization. What I mean by that is that, let me actually draw this structure again. So you have suppose gallium and you have nitrogen, you have nitrogen, you have nitrogen and you have nitrogen. Because there is a negative charge here and a positive charge here, the electric field will be in this direction between these two bonds. Okay, the field, by definition the polarization field is in the opposite direction. Okay, so the polarization field is in this direction, I call it P naught. Electric field and polarization are in opposite direction. So there is a polarization like a slight negative, slight positive. So there is a polarization going from negative to positive. So there is a polarization going from negative to positive, there is a polarization going from negative to positive, there is a polarization going from negative to positive. If you take the cos and sine components, then all the lateral component they add up to 0, add to 0. However, the vertical component, if you take the sine and cos component, because they are at an angle, no. So if you take the sine and cos angle, the total lateral component adds up to 0, but the total vertical component does not add up to 0. So in other words, the total there is a net polarization in the z direction, where the top of this cell behaves like a negative and the bottom of this behaves like a positive. Okay. So there is an electric field in this direction, which means the polarization is in this direction. The total polarization of the unit cell of this tetrahedra will actually be in this direction, the field will be in this direction, and so one layer of gallium nitride, if I take, the top will be negative, bottom will be positive. Okay, one unit cell. Okay, it will look like top is negative, bottom is positive. The value of this, and this is equal in magnitude, this is minus sigma p, this is exactly plus sigma p. Okay, this is exactly minus sigma p, this is exactly plus sigma p, and both of them are equal in magnitude but opposite in sign. They are opposite in sign. The unit of this is charge per unit area, and I can call it per centimeter square, because if I take a wafer per unit area, what is the charge density basically. So that is the unit of the polarization. So this is called spontaneous polarization, because it exists always in gallium nitride and its alloys. So the spontaneous polarization value of gallium nitride is minus 0.029 coulomb per meter square. You can say centimeter square, meter square, does not matter. And bottom is plus 0.029 coulomb per meter square. That is the number, that is the charge. That is, so you have to remember that this negative and positive charge is precisely a dipole kind of a charge. It is not mobile charge like electrons or holes, it is not mobile. It is also not ionized impurities, immobile ionized impurities, no. It is not ionized impurity, it is not mobile electron or hole, it is just a dipole charge. But I can say that this charge of say 0.029 coulomb per meter square, what is its equivalent, what is it equivalent to in terms of number of electron? If there were electron, how many electrons would accommodate this charge? So you have to divide by the charge of electron by Q, which is 1.6 into 10 to the minus 19 coulomb. Okay, so if you do that, it will come up to be around say 2 into 10 to the power 13 per centimeter square. That is a very large number of electron per unit area. It is a very large number of electron per unit area that you are actually getting the charge. Okay. So this is a very different, unique and interesting property of gallium nitride, okay, that helps make gallium nitride transistors HEMTs without even using any doping. Okay, without even using any doping. So now if I take one layer of gallium nitride, so there is minus, there is plus. If I take another layer, there is minus, there is plus. So this plus and minus will cancel. Then I have another layer, minus, plus, this minus and plus will cancel. So all the interfaces, okay, if I have multiple layers of gallium nitride and the total thickness is suppose 100 nanometer. So all interfaces plus minus they will cancel out. They will cancel out. Only at the top you will have minus and at the bottom you will have plus. only at the top you will have minus, at the bottom you will have plus. Rest inside they will all cancel out mutually, top bottom top bottom. Okay. So, this is your the layer of gallium nitride has a negative charge at the top, a positive charge at the bottom, okay, and the value of the spontaneous polarization is 0.029. Similarly, for indium nitride also the spontaneous polarization is actually much different, it is minus 0.032, it is not much different coulomb per meter square. Aluminum nitride has very high, the spontaneous polarization of aluminum nitride, okay, is actually minus 0.081 coulomb per meter square. That is a very large, almost 3 times larger than the spontaneous polarization value of gallium nitride. So, aluminum nitride is extremely polar because of the distortion of the crystal and the electronegativity difference that I talked about. Okay. Now, this is all fine. Okay. This is all fine. This is called spontaneous polarization, and the way the crystal can be arranged, by the way, this is a common knowledge, you do not need to know so much, but the way the crystal is arranged, there can be 2 orientations of gallium nitride. Okay. What I mean is that there is gallium polar, which whatever we talked about till now is actually gallium polar gallium nitride. There is also a reverse polarity of gallium nitride, which is called N polar gallium nitride, which means if you have a gallium nitride crystal, okay, if you have a gallium nitride crystal, say you have this gallium, then you have nitrogen, 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 okay, nitrogen here, nitrogen here, nitrogen here, nitrogen here, okay. If you invert if you flip the crystal upside down, it will not be the same. If you this is a hexagonal of course crystal, I am just drawing a unit tetrahedra, but if you do a flipping upside down, you will have nitrogen with which you are bonding gallium like that. Okay. So, this is your N polar, and an N polar because you are flipping it upside down. So, if I take a piece of gallium nitride, the top is negative, the bottom is positive. If you flip it upside down and it is still gallium nitride, but many properties have changed including polarization. So, the top is positive and the bottom is negative. This is called nitrogen polar or N polar gallium nitride. There has been a lot of research on N polar gallium nitride also, but we will not discuss this in our course because as of now there is no commercial RF device based on N polar gallium nitride that is there in the market, but it could be internally used in the US military for instance. So, there could be internal market, there could be internal supply, but not that we are aware of in the public domain, but in general commercially there is no N polar devices. It is very useful or promising for super high frequencies such as W band, which is say 94 gigahertz. There are many military applications, and for that people have shown that nitrogen polar gallium nitride HEMT could be superior to a gallium polar gallium nitride HEMT. But that being said, majority almost everything is towards gallium polar. So, we will only discuss gallium polar HEMTs in this course. Okay. So, gallium polar orientation of your crystal, of the crystal is what we will talk about. So, now the last thing that we will discuss in today's class before we end the lecture is the fact that I told you that there is a, if I take a gallium nitride crystal say 100 nanometer, there is a negative charge at the top and a positive charge at the bottom, and in between there is nothing. So, if you have a negative charge at the top and a positive charge at the bottom, this is suppose the x axis, then the electric field, there is an electric field, there will be an electric field between in this region because it is a dipole. Between the dipole there is always going to be an electric field. So, what it means is that if I draw the energy band diagram, if I draw the energy band diagram of a HEMT, it will look like something like that: conduction band, valence band, Fermi level, because there is always going to be a field due to the presence of a dipole, negative, positive, okay, that is the dipole. However, there is a limit to the thickness over which you will see this. You will not see this over arbitrary thickness. Okay. The reason is, suppose your gallium nitride is very thin. So, you have something like that, this is conduction band, this is Fermi level, and this is a valence band. Once you keep it increasing the thick, this is Fermi level. Once you keep increasing the thickness, it will soon hit this, okay, it will soon hit this. Okay. After that what will happen? The entire band gap has dropped, okay, the entire band gap has dropped. It cannot go like this, it cannot go like that. because extra holes will generate here, okay, extra electrons will generate here, extra holes, sorry, extra electrons will generate here, extra holes will generate here, that will compensate for the dipole, okay, that will compensate for the dipole, and it will basically pin the Fermi level there. So, beyond that this compensating dipoles will appear, electrons and holes will appear, and the bands will become flat, okay, the bands will become flat. Or you can say that if there is a Fermi pinning on the surface because of a defect, the band will look like that and it will look flat. There is a defect level here ED at which the Fermi level is pinned, okay. So, all the way the valence band could not reach the Fermi level, there is a defect level that pinned the Fermi level. So, it is a band bending like that and then it is like that, okay. So, this is flat. So, which means you cannot have the entire 100 or few hundred nanometer dropping the field, you know, it only around 20 or 22 nanometer in which the field will drop if it is band gap to band gap. If it is defect, it is even less than that, and then beyond that it will be flat. So, essentially compensating dipoles will appear and it will not allow the bands to drop or bend indefinitely. That is an important thing you need to know, okay. That is a very important thing because it will put a limit on how thick you can have gallium nitride before the fields will not drop across the entire material. So, what I mean is that if I use a 1 micron thick gallium nitride layer, it does not mean that the entire layer has a field, that is what it means basically, okay. You just keep it in mind. And the last thing before we conclude this lecture is that all this was spontaneous polarization. There is also something called piezoelectric polarization, and piezoelectric polarization arises because of the stress or strain. So, for instance, if you try to grow aluminum gallium nitride on top of gallium nitride, then this layer of aluminum gallium nitride is under tensile stress. Why? Because I told you already the atomic spacing between the aluminum nitride AlGaN atoms is actually smaller than that in gallium nitride atoms. So, you have to squeeze this up, you have to pull this out. So, that is your tensile stress. When you have a tensile stress or even if compressive stress, any stress, in this case it is tensile stress, that stress gives rise to a piezoelectric component because these are piezoelectric material. In piezoelectric material you can apply a voltage to get a strain, or you can apply to strain and get a voltage. So, that is what is happening, you have a strain here because of this lattice mismatch, and that is why you can get an additional component of piezoelectric polarization, we call it sigma Pz. So, in tensile stress the piezoelectric polarization will have the same direction as the spontaneous polarization, which means the piezoelectric polarization because of tensile stress will add a further negative sign here and a positive sign here. In top of this is because of the sigma piezoelectric polarization. This is in addition to a spontaneous polarization negative on top and spontaneous polarization positive at bottom. So, it is going to reinforce the total negative on the top and total positive at the bottom interface of AlGaN, okay. It is going to reinforce that, and it is because it is a tensile stress. Had it been a compressive stress, it would have been opposite. So, if you instead of AlGaN, if for instance you had InGaN, suppose indium gallium nitride. In indium gallium nitride the stress is not tensile, it is compressive. So, compressive stress means because indium gallium nitride has larger lattice constant, so you push it inside, it skews it up. In compressive stress what would happen is that the direction of the polarization for piezoelectric component would be opposite to that of the spontaneous. So, the spontaneous has minus here plus here for AlGaN, this is spontaneous. The compressive polarization would add plus here, this is compressive, and a negative here. However, this value would be very large, much larger than this. So, it would overwhelmingly make it positive and it would overwhelmingly make it negative, okay. In the case of AlGaN GaN, this overwhelmingly top is negative and the bottom is positive. In the case of InGaN it would be opposite. So, this is about compressive strain and about tensile stress. So, today we will end the lecture here, lecture 6, okay. We will continue in lecture 7 about gallium nitride's piezoelectric polarization. We will look at the expression for polarization, piezoelectric polarization. We will work out some simple band diagrams to understand how the band diagrams look like for InGaN GaN, AlGaN GaN, AlGaN InGaN. It gives you an insight into how to draw band diagram, okay. And then we will move to an AlGaN GaN Hempt band diagram, and we will talk about the electron gas, a 2D electron gas at the AlGaN GaN interface, which is at the heart of Elgan-GaN-HEMT. And Elgan-GaN-HEMT, as I told you earlier, is penetrating the market rapidly for both civilian and strategic sector in RF electronic applications. Okay, so we will talk about gallium nitride alloys and heterojunction and HEMTs in the next class. Okay, till then, thank you.